And you're all very quiet today. For the Socrative questions, feel free to talk to each other, use each other's brain. Yeah. All right, do we have the final answers on this one? Best guesses? Last chance. All right, very good. Right, so if we just put our values in here, that 200 mils for the volume, 7, 8, 9 grams per mil here. Mils cancel out, and our answer is left in grams at 157.8. All right. So, understanding that a protein and carbohydrates contain 4 big calories per gram of energy, and lipids contain 9 calories per gram. How much energy does a snack that contains 5 grams of fat, 7 grams of carbohydrate, and 3 grams of protein contain? And do we have all the responses on this one? And last chance. All right, very good. It was 85 calories, right? So if you have 5 grams of fat, right? The conversion for that is 9 calories per gram, right? So you've got 45 calories for the fat, and then for the protein, we had 3 grams of protein, and that's at 4 calories per gram. So there's 12 calories for our protein, and we had 7 grams of carbohydrate, also at 4 calories per gram, 28 calories. And then add those all up together. All right, so you can convert any of your food based on its mass, right, into the calorie load or energy load that you would be consuming at any one time. Great. All right. So here, a patient needs to take 875 milligrams of ibuprofen twice daily. The pills in the bottle are 250 milligrams each. How many pills does the patient need to take each time she wants the 875 milligram dose? Assume that the pills are scored, so you could cut them in half if you need to. So what is your conversion factor here? What do you need to know in the question? What do you need to know? Yeah, what do we need to know? The number of? How many pills, right? So we need to know the pills. Right? That's what we need to find out. And we know what is the conversion factor for one pill? 250, right? 250 milligrams? One pill is 250 milligrams, right? We want a dose of? Yes. Right? So we need to use our conversion factor to find out how many pills we're going to get. Right? So pills needs to go on top. Right? And so that is a single dose. Right? And they would need to take that dose twice a day. Well, what is it asking you for? How many pills does the patient need to take each time she wants the 875 milligram dose? Yep, so this should give you your answer if you do that math. Yeah, so anytime you're doing conversion, you will, what you want should be on the top of the conversion. What you have should go on the bottom so that you cancel it out. Right? So milligrams here is going to cancel out, and we'll be left with number of pills. If we flipped it the other way, we would have milligrams squared over pills, which makes no sense for our dosage.
Was I supposed to?
What unit is left? It's just pills. Yep. All right. Do we have all the answers in? That's a lot of pills. A lot of pain. Yeah. All right. So I think I heard answers out there of like 3.5 pills. Very good. All right. Here is a drop one. You need to give a patient 1,000 milliliters of the drug D5LR by IV, intravenous injection, over an 8-hour period. The drop factor is 20 drops per mil. How many drops per minute should be administered? This one, a little more involved. Right? So what do we want at the end? Drops per minute. Right? So we need to get GTT over minute. Okay? So we have an 8-hour period. So our time is not meshing at the current moment. How do we need to change our time? If we need to get it into minutes? Yeah, we need to convert our 8-hour period. Right? Times, we know 60 minutes per hour. Gives us what? 480? All right, so we have 480 minutes. So we know kind of what that bottom is going to be using. All right, so now we need to figure out our drop factor, right? So we know we have to administer 1,000 milliliters, right, of our drug. And we have a conversion between that volume and the drop factor, right, of what? 20, right? So we've got 20 drops per mil. So we can figure out that top part. We have 1,000 mils of our drug, and we're going to drop it 20 GTT per mil, right? So what is that going to, how many drops are we going to need? A lot of drops. 20,000, yes. 20,000, whoa, 1, 2, 3, 4, drops, GTT, right? And the time that we need? 480 minutes. We need 8 hours, right? Equals. Hopefully it's up there.
Don't say nothing like that.
All right, we have all the answers. All right, 100%. Good job. All right. Okay, let's go back to our lecture. All right, so last time we got through precision and accuracy, so that leaves rounding and significant figures that we need to get through today. So in chemistry, we use a concept called rounding to the evens, which may be a little different than you've been used to before, because we tend to round up when we have 5. And if it's money, yeah, you always want to round up, right, and have more money, right? But with chemistry or other data collection systems, any type of science that you might be doing, if you always round up with 5, you're going to bias your data set, right? Because sometimes you should round down, right? It's right in the middle, so why always round up, right? So the rounding is the same essentially for the numbers below 5. If you have below 5, you're going to round down. If you have above 5, you're going to round up. The rounding to the evens only happens when you have exactly 5 that you need to round, right? So sometimes you need to round it up, and sometimes you need to round it down. And so that's going to depend on the even, right? So if your digit that you need to round is exactly 5, like it's shown here, we're rounding to the next position back, right? So if that number is even, that's next to the 5, you're going to round to that number. So this one would round down in this case to 51.6 if we were rounding that 5 position. All right, but if the digit is odd that's next to the exact 5, and we need to round to that position, we're going to round up to the even, right? So the next even would be the 8. That's rounding to the even. That's the only difference is when you have exactly 5 that you need to round up or down, round it to the even number. Right? So if you have an odd number that's next to it, you need to round up. If you have an even number next to it, you're rounding down to that number. Does that make sense? All right. So that's the only caveat for rounding that you'll have in here that is different from rounding that you may have seen previously. It's when you have exactly 5 that you're going to round to. So just if this number was, right, 51.652, 52 is bigger than 5, right? And so in this case, you just round up, right? So if you had to round back now to this spot as well, if you have a 2 in that position, that makes the 5 bigger than 5, right? Because you have 5, 2 right there, right? So you would round up to 51.7. Right? So if you're greater than 5, go up normally, round up. If you're below 5, you're going to round down. If you're exactly 5, round to the even. Does that make sense? Okay. We'll get some practice. So, right, this number, that number is bigger than 5, right? So you round up. This number is smaller than 5, right? If I have to round back to this position, that 4, right, that is smaller than 5, right? I have 5,000, like it goes all the way out. We would round down to the 6. Only when it's exactly 5 do we need to worry about rounding to the evens. All right. Okay. So the next hurdle, and this one is difficult. This is kind of a hard concept to really wrap your mind around while you're doing measurements is significant figures. You can't just put your calculator dump onto the paper, right? So we need to have measurements that have significant figures. So every piece of instrument that we have in the lab, including our eyeballs when we're making observations, is limited to the instrument that we're using to measure it. So it will only have a certain distance out that we can go out and have any accuracy on. So for significant figures, you always have to go out to an estimated position, and that is your best guess position. And then you can't go out farther than that. Once you have to start guessing, you have to stop, right? So if we're looking at this ruler, right, so this ruler is out in positions of 0.1, right? So I can see definitively 0.1, 0.2, 0.3, 0.4, 0.5, all the way up this ruler, right? So that's the tenths position, right? So my guess position will be the hundredths position, right? So if I'm measuring this thing, right, I see it falls in between these two. So I know it's falling in between 1.3 and 1.4, right? So I need to guess how far between those two I think it is, right? So I think it's a little bit closer to the 4 than the 3, right? So I'm going to say maybe 7, right? So that's my best guess. Your best guess might be 6. Your guess might be 8. I don't know. So, but I would say that this is 1.37, right? And that would be my best guess, right? So that number has to have those 3 significant figures. If I just put 1.3, I'm not using my measuring device correctly, right? Like it needs to go out to that guess position. And even instruments that are digital, like a balance or something that you have in the lab, you'll often see like when we're in the lab and you put something on the balance, like it kind of floats and you're like waiting. You're like, is it gonna ever like quit moving around? That last position on the balance is the best guess. So it's going, oh, I think it's like 0.6, oh, but it might be 0.4, but it might be 0.5. And you just got to take a reading and go away, do your other things. So all instrumentation has a position of best guess to it. And that's where you have to stop, right, for your significant figures when you're making measurements in the lab. So when we're doing calculations and things, we have to pay attention to the significant figures that are in our problem sets and make sure you don't give me a number like 1.378955627 centimeters, right? Because that's not accurate. Like you can't go out that far and have any idea that that's actually the position that you're measuring. So that's significant figures, right? So and even our balance, right, that last position on the balance is the best guess of the balance, right? So that's its estimated position. So when you're evaluating someone else's data or measurements, you have to be able to identify the significant figures in the number that you're looking at and be able to use that data sometimes in calculations, like we've been doing these problem sets. We haven't paid attention to significant figures yet, but we will as we move forward with your calculations. So there's rules around significant figures, right? So trailing numbers at the end of a number, but to the left of the decimal, may be acting as placeholders. So if you're using measured numbers, like the person who gave you those measured numbers would have to tell you if those zeros are significant or not, or you assume that they're not significant, right? So if you just have the number, you have to assume that they're not significant and not count them towards your total, right? So if I have the number 800, sorry. This number, right, could have 3 significant figures, right? That would be if these are placeholders and those are not significant. Truck scales might be like this, right? You see truck scales on the side of the road, they drive off and they put their truck on there. You may not be able to tell to the pound how heavy the truck is, right? That's not accurate. Its best guess is actually at hundreds of pounds, right? So that's how far you may be able to go out. It could have 4 significant figures if that first 0 is significant, or it could have 5 if both zeros are significant, and that's the actual measurement that was made, right? So I would have to tell you if it's significant. I can do that in one of 2 ways, right? I can put the decimal in. If you put the decimal place in, that means all the numbers are significant in that number. So this would say you have 5 significant figures. I can also put a line over a 0. That would also indicate that that 0 is significant, but that one's not, right? So I have 4 significant figures in that number. I could also put my number in scientific notation. And any numbers that I show in scientific notation are significant. So if I show those zeros in scientific notation, it means they're significant. If I don't, if I just put 3.98, it means they're not significant for the number. So you've got those 3 different ways of showing zeros could be significant, right? So this is if they're trailing a number, but to the left side of the decimal place. All right, that's our first rule. More rules. All right, so all non-zero digits are significant. That's pretty easy. So 171 has 3 significant figures in it. Trapped zeros between non-zero digits are significant. So 1004 has 4 significant figures. Those zeros have to be significant. Any trailing zeros after a decimal place are also significant. You wouldn't show them unless they're significant. So if you see them past the decimal place, you count them towards significant. Except in this last case, where they're before the number, right? So if I'm listing out before the number, this number only has 2 significant figures. Okay. So these guys are all placeholders. All right. That's our rules for significant figures. Not too bad? All right. So our first question here, when you're conducting an experiment, this is going to get back to accuracy and precision. You repeat your procedure 3 times. However, on the 3rd time, you spill some of the mixture when you're walking across the lab, and this trial does not match the other 2. This would represent a lack of accuracy in the data. True or false? I know we did this yesterday. Whoop. So if I show you your bullseye again.
Versus like got 2 sevens and a 6.
Yeah.
That's my opinion.
Which means for measuring across.
Right.
The other one doesn't say nothing about the measurement. That one says measurement.
I mean, the data doesn't have
All right. Do we have all the responses? All right. We're 50-50. Yeah, so this one is a lack of precision. So it's your precision in being able to make repeated measurements, right? So that you get a nice tight window. So remember, we said you could be precise and not accurate at all, right? So if your instrument is not calibrated, you could have very good repeated measurements, but still be way off from the accuracy of the measurement. Will lack of precision make your measurement inaccurate? Yes. But it's fixable by the precision element. All right. Hopefully these guys are a little bit easier now. So how many significant figures does the following number contain? And we have all the responses. All right, this one has trapped zeros. That means they are significant. So it is 4 for this number. How about this number?
I know, but this stuff is way better. I know sometimes because I think the tumors anatomy and like most of them are still or just so there's a lot of
And we have all the answers. Last chance. Best guess. All right. This one has 3. So the 3 significant figures in that number are the last 3. So if you show that last 0, it has to be significant. The leading zeros in this case are not significant. They are placeholders.
Oh wait, if she didn't specify, so I think she goes right. I just scored get one wrong. You know, because she's in these, she indicated a decimal.
Yeah.
It's a tricky one.
I think you're right with that one.
I'm pretty.
I think you ate that down without one actually.
I'm still not confident.
I'm submitting that with you confident because I believe
Hey,
it.
I'm agreeing. Research will not indicate to us what the significance is.
There's no decimal, there's no nothing.
There's no dash, there ain't no.
And she didn't tell us nothing about the commas with the zeros.
You're on
Look at it, yeah.
She's like, you're on a sleep.
She gives me confidence. She's smart. But she gives me smiling like,
All right, we have all the responses.
she's like, that's a great idea.
Maybe next time.
All right, the answer in this case is only 3. So unless you're told that those other zeros are significant, you have to assume that they are not. Right? So if you read this in a paper and wanted to use this in a calculation, you have to say there's only 3 significant figures in that number.
Then I'm only gonna put those
Yeah.
3 in the calculator.
No, you use the whole number. It's still 432
Whatever.
million.
Yeah.
Right? So you have to use that number if you're doing a calculation. But you have to round it back to 3 significant figures in your answer.
Like 2006.
Yeah, so if you get some number calculator dump that goes out 9 digits, you got to get rid of 6.
Okay.
Yeah. Yeah, even if you round them back to zeros.
Would you put that into scientific notation?
Yeah, you could put it into scientific notation to show zeros are significant or not. Yeah. That would be a better way to show that number. How many significant figures does that number have currently? Yes, it has 5, so you've got to round it back to only having 3.
It's like the one before the decimal point count as like 1, 2, 3.
Yes. So you have to round back to this base, right? Using the numbers after it. Yes. So what are your rounding rules? Greater than 5, round up. Less than 5, round down. Exactly 5, round to evens. Yeah, so is this number exactly 5?
Wait, but does it matter if the, do we still look at this as like even, is it still like 5? If it's exactly greater, but why would you?
Yes.
But if it was just 5 at the end, then it would be that even.
Correct. So if you're looking at the number that's past that, right, that's bigger than 5. Not by a lot, but a little. It's a little bit bigger than just 5. So you have to round up.
Okay, so 5?
This number is not exactly 5.
Oh,
That whole thing, whatever is past where you need to round to. Yeah.
okay. So we're not just like that.
Yeah, so you're like, pay me more money. Round up. Yep. All right. Do we have all the answers in there? Last chance? All right, so that's a round up situation.
Oh, now this is the
But it's just 5. So this one is, okay. Okay, I see.
Yes.
I see.
This one, and it gives it 6.3.
Yeah. Yeah.
What do you think that is?
Because there's no number after. I thought the 6 just didn't matter. I thought it was just 0.
But it does matter.
But it's like 5. Yeah, I didn't understand. But she's saying now it's not just 5. You're
Yeah. That's why 6 is
Okay. I'm so forward to it. Yeah, have Gabby's name. She was
Big
like,
things. So you don't say significant.
like for the first one, this one is just 5. So we're gonna leave this in that it should say round one. We just leave it right there. We just need to
because
3, 4.
technically in normal rounding, we don't have to see because she was rounding down.
Because it's just
5. There's no 6 after it.
I feel like I'm ready to go. That has like all of my equipment and all of my rooms. With the table. Yeah.
Do we have all the responses?
Wait.
Page 2.
Okay. I'm gonna say B.
Last chance? All right, so this is a case of rounding to the evens, right? We have exactly 5. Right, there's no number past the 5 to make it larger, right? So we need to round to the even. So the number before is even, so we would round down in this case. Yeah, so you need to round this one to 4 significant figures.
But it's higher than 9. Or it's higher than 5. 94. So it would be 7.
Why B? Give me an argument.
Yes. Mathematics.
Don't do that.
Like second and D. About what?
That, because we wouldn't round that.
Yeah.
We ain't rounding that.
We ain't rounding it because it's not higher. 5 or higher.
What else did we did round?
Why are we rounding?
Because the 94 is higher than 5. That you gotta go with 12.
Okay.
Because,
I'm with it now.
because like these are our 4, so these ones kind of don't matter, but they represent like if you're gonna go higher than 5.
Right.
The 94 does, it's higher than 5.
Right. Okay. Yes. Okay. Okay.
You know, I actually used to hate rounding when I was young. It was really hard for me. Like rounding in division, I just never did good. And then we come to chemistry, it's just rounding. I'm like everything I hated about life, like.
And we have all the answers.
I'm like, if we did graphic,
Last chance. Best guess.
This is exposure.
Very good. 98% here. You round up, right? The 9 is bigger than 5. So you're going to round that position up to the 4. We haven't done these yet. We'll hold this one. 9 is bigger than 5. Yep. All right. So we've seen the rules now for rounding and for looking at numbers and figuring out the significant figures in them. So now what do we do if we are doing things with those numbers, right? We've got 4 things we can do with those numbers. Well, we've got more than that, but we're going to focus on 4. We've got addition and subtraction, and we've got multiplication and division. You could do logs and all kinds of weird things too, but we're not going there. Yeah, so if you have multiplication and division, right, you're looking at your numbers the first thing you need to do is evaluate your numbers for the significant figures and identify the fewest. Right? So this number has how many significant figures? Right? Which is 5. Right? So there's 5 there. And the other number has 3. Right? So our fewest is 3. That means our answer has to have the fewest, 3. So we have to round back our answer to 3 significant figures. Right? So do your calculation with no rounding. And you write down your calculator dump for that number that you get, right? And then you have to round back to 3 significant figures, right? So it's going to be 1, 2, 3. So you've got to round back to the ones position in this case. This number here is below 0.5, right? So if you put the 0.5 here, 0.4072 is below 0.5. So we are going to round down. So we're going to keep that 0, right? So 280 is the final answer. Can I show it that way? No. What do I need to do to show that that 0 is significant? Decimal place. That would be a fine thing. So I can write 280 with the decimal. How else? I can use my dashed line like that. Or I can put it in scientific notation and keep it in the scientific notation. Yeah, so you just have to show if that 0 is to the left of the decimal place. If it's significant, you have to tell me. All right, so that's multiplication and division. Find the fewest significant figures and keep that in your final answer. So you may have to do a lot of rounding. Sometimes the rounding doesn't feel good. Yeah, like if you have to round to like the hundreds position, it feels bad to like take a number like 642 and round it to 600. Right? But sometimes you have to. That's your significance. All right. For addition and subtraction, we are going to look a little bit differently. We're going to look past the decimal place or the farthest position over, right? And we're going to keep the least position in the decimal place is going to be our significant place. So usually for addition and subtraction, I like to line them up, right? And then it's easier to kind of look at these, right? So we have 17.098 plus 16.4, right? If we're looking for decimal place positions, right, we can see that one's position, or the tenths position, right, is the place, right? So that's where we have to round to in our final answer. Just this one position, right? So the least place past the decimal in your number for addition and subtraction. Do the whole thing. Get your full number. So do your calculator dump first. And then I know I have to round it back to that 4 position. So you're rounding that 9 back. 9 is bigger than 5. So we need to round up at this place, right? So we'd get 33.5 as our final answer. Right, so for addition, subtraction, if it's easier to line it up on top of each other, and then you can just draw your down where you're past the decimal. Always do your full calculations first before you round. What happens if you have both things in an equation? Sometimes we do both things, right? We multiply, we add, we subtract, we divide. It could all be in the same equation, right? You've got to follow all of those rules, right? And use the least significant figures. So you got to evaluate for multiplication, division, evaluate for addition, subtraction, and then whatever is the least, that's what you're going to go with in your final answer. But if you have multiple calculations, do all the calculations first and round at the very end. Don't round in the middle. You bias your data set if you round in the middle and then do more calculations with a rounded number. So there are also some numbers that are exact numbers. or their standards that we use, those do not count towards your significant figures. Like if we're counting people in this room, that's an exact number. So that would not go towards significant figures. That's not a measured value, right? Like you don't have an estimated guess. Well, I could guess how many people are in here, but I could count and I know exactly how many people are in here. I'm not going to say it's 52.3 people, right? You can't have a 0.3 person, right? So that's an exact number. Or if you have pencils or pennies or whatever, that would not go towards your significant figure count. Only measured values count towards significant figures. Okay, so defined conversion factors that you might be using. 1,000 milligrams equals 1 gram does not count in your significant figures, only the measured value. So if I gave you 23.6 milliliters and you're doing conversions to liters, you still have 3 significant figures in that 23.6 milliliters. You have to keep those 3 significant figures. That's your measured quantity. The conversion factor is a standard. Does that make sense? We'll get practice. Yeah, doing that. All right. In fact, maybe now.
Oh, this?
So we've got 14.328. All right, so if we line it up like that, our addition, subtraction, will tell us where we need to round to.
Yeah, I think that was a good choice. Or D.
And we have all the responses. Last chance. All right, so in this case, we round down because that 2.8, right, that's below 5. So we would round back. All right, this one is subtraction. So same method that we used in the last problem. So rounding back to the hundredths position here.
I did. Are you gonna get like regular parts? You're gonna get one with the heart one? Yeah, people be getting like the ladybug with the hearts. Where are you gonna put your bike food? That's what I call them.
You know what?
I sometimes forget
The day before that, April 24th.
Yeah.
Noah Khan.
What did I be?
Zaba.
Yeah.
Wait, I'm not ready.
I put
Who was your mind?
I was sobbing in the end of the sobbing. I was sobbing.
Oh,
Did you go
for me.
No, in the theater. What?
And do we have all the responses? Best guesses? Last chance? All right, so we got 3.99 on this one. So the next, if we had to round that back to the 10th position, that's where it might feel uncomfortable, right? Like, so if we had to round 3.99, right, back one more position, like if we had to round it back to that position, what happens? Yeah, so if we had to round it to the 10th position, it would turn into 4.0, right? We have to still keep that 0 present. That's still significant. But if we round 9 up, 9 rounds to 10. Right? So if we're rounding 9 up, it rounds to 10, which is going to push that next number up that's next to it. So it would make the 3 a 4, whoop, and put the 0 from that 10 in the 10th position. So that happens sometimes as well. All right, now we have multiplication.
So we need 2 because it's the longest. Give me 2. Oh, it's gonna be 1, 2. So
Which feels sucky. Yes, but that is correct. So you need to round this back to how many significant figures? 2. What is your calculator dump? All right, so we need to round it back to 2 significant figures. So this number is 275, right? You can't round it back to 28. That's a very small number, right? You got to keep the ones position in there. If somebody was paying you back and they were like, I'll just round up, you wouldn't want them to give you $28. Right? You'd be like, wait, where's my $275? Yeah. So this number next to it, is that exactly 5? Is it? No, because there's stuff after it, right? 5.032 is greater than 5, right? So you have to round up. That happens to also be to the even, so that's fine both ways actually. But yeah, so you would round this up. Okay, do I need to do anything different to this number? No. Right? Because only the 2 and the 8 are significant. The 0 is not significant. All right, so 280 is your answer there. And the last one. 35.4 divided by 4.0. Oh, sorry, I inverted my number. Thank you. You'll get the wrong answer if you use mine. How many significant figures do you have?
2.
2 is your limiting, right? This one has 2. This one has 3. So we go with the least. Well, there's only one answer it could be up there. There's only one answer with two significant figures in it. Yeah, so sometimes you can figure out the answer if you know, oh, it can only have two significant figures. Last chance. All right. Yeah, so rounding, we had to round to two significant figures. Was your calculator dump 8.625? Yeah, so rounding, right? I know I need to round to this position. So I'm looking at the number right next to it. It's 2. 2 is below 5, right? So we need to round down. Yeah. Good. If we were rounding to 3 significant figures, right? We would be rounding to this position, and we have exactly 5, so we would round to the even. So it would stay at 8.62. Yeah. Good. Let's take 5-minute break. If you're in the online lab, I have a piece of equipment for you for next week's lab if you want to pick it up today. And check it out. This is only the online lab people. The other people will have this in the lab. There is an online lab. Are you online? No, I'm not. What's your name? Taylor. Yes.
Yeah. The nucleic acid super.
Yeah, if it's full, yeah. Are you in the online? All right. Okay. Yeah, once you're switched in, I can get you checked out for that.
Sounds good. Okay, thank you. Do I come during your office hours to pick up the material then?
Oh, yeah. You were able to sign up for the class without signing up for lab?
No, I signed up for the Friday one in the evening, like around 2, but I can't still work. So I rather do the online one.
Yeah, you should just be able to drop the regular lab and sign up for the online one. Yeah. For this week, though, the handout's the same for both.
Okay.
So you can just download the assignment in there and you can complete it on your own if you can't make it to the afternoon lab. Okay. Does that sound good?
Yeah, thank you.
You bet.
Hi.
Yeah.
Here Monday because I was in California.
Yeah.
And I didn't get to do this thing.
Yeah, they're in class problems. So I do drop your lowest score.
So like if I'm missing one, it should be okay.
It should be okay. And I'll post blank ones in there too. I haven't got the grades in for Mondays yet. but I'll post a blank one in there too, so you can have it to study from.
Okay, cool.
Yeah,
Thank you.
you bet.
Mine gets decent mileage, but it's not as good as it should be. I need to replace the air filter and it'll get way better.
Wait, what? I took that. Hybrid. Class was 4 to 6. Oh, that's new in my at the bottom. You started it.
All right, so we are ready to jump into chapter 2. So chapter 2 moves a little bit away from the math. Like that math overview will help us in the lab and help us throughout the term with calculations that we'll be doing that's more related to the chemistry components. So in this first chemistry section, we're going to talk about the atom. We'll learn its structure and then how it relates to the periodic table and how useful the periodic table is. Okay, so we're going to start talking about chemistry and matter, the scientific method, then get into atomic theory and how they relate to the different elements that are on the periodic table. We'll define the atom, and then we'll look at some periodic table trends. So chemistry is really a central science. And we also see that math and physics are also central sciences as well, which is kind of why we started with that math component. Chemistry then branches out to really everything else, right? Because chemistry is really the study of matter, which is everything that everything is made up of. So if you want to study anything about, what things are made up of and how they interact with each other, you're going to get into aspects of chemistry. So really that affects all of these areas here. And in this class, we're going to kind of be focused more on this area. So we're going to get into some organic chemistry, which are compounds that make up living organisms, and then really how that affects the biochemistry in those systems, how proteins and maybe drug molecules are interacting together, and then the class will be over, right? I'll be done with it. Okay, so that's kind of where we're going with our trajectory. So matter is defined as anything that occupies space and possesses mass, right? So any type of weight that is in a system. So that could be a material that we make, right? Like a chair or the desk or the table. It can be something found in nature like a rock, or it can be a living system as well. So all of these things have matter that are associated with them and take up space and have mass. So chemistry is really focused on studying things that have matter, right? What are things made of and how can we tell and what properties does it have? So anything that has matter has a set of properties that have both physical properties and chemical properties that are associated with them. So the physical properties are going to be characteristics that describe the matter that don't change the matter, right? So these are things like a boiling point or a melting point. so that can cause phase changes. Obviously, we won't be talking about people when we're talking about phase changes. We can't do that, right? We know that's very bad for us to do that. So things like temperature are going to be very important for phase changes. Other things such as color or luster or flexibility of the compound, that's going to be physical characteristics that you can look at and you can measure, right? So the other characteristics are chemical properties, right? So these describe how reactive a substance is when it's going to interact with another compound, right? And so things of this nature would be things like chemical stability, the flammability, anything that's going to change the chemistry of that matter into something else, right? So oxidation states, how toxic is it? It's going to be interacting with biological systems, and possible chemical bonds that can form with it. Those would all be chemical changes. Sometimes those are hard to discern what's happening, if it's a physical change or a chemical change, but we'll talk about some of those examples. So when we're talking about matter, we can start breaking it down smaller and smaller components. So the first level is called a substance. So this is going to be any sample of matter that has the same physical and chemical properties throughout the sample. So they can be of two types. It can either be an element or a compound. You could think of this as elements are all on the periodic table. So if you had a sample of gold and it was pure gold, that would be an elemental sample and that would be a substance, right? But people have water bottles here, right? If you have pure water, that's a compound that's made up of hydrogen and oxygen, H2O, right? That would fall under the compound, but it also can be a pure substance, right? So it's made up of more than one element, right, coming together. But it's pure. Nothing else is in it, just the water, right? Unless you have salts and minerals and things that you've added to it. Yeah, then there would be multiple things. So the periodic table is a way that we can categorize all of the elements that are found on the planet or in the universe as far as we can tell, right? We haven't found additional things in here. And some of these we've made like in a lab for like a nanosecond, like, and then it's gone. Like they're so big, they're so unstable, we don't really see them very much. So that's really like these guys here that are in that kind of tan color. We found them in the lab in just a microsecond, and then it's disappeared. All right, so these are substances that cannot be broken down chemically into simpler components. So all the known elements are represented here. We've identified 118 so far. All right, so our compounds, we said, are substances that can be broken down into chemically simpler components. So we used water as our example, H2O, right? These are atoms of hydrogen and oxygen that are going to come together in specific bonds that are sharing. But we can see that we have two atoms of hydrogen and one atom of oxygen that have to come together to make up that water. So the water can be broken down into simpler components or the elements, right? Once you get down to the element stage, you really can't break this down farther, right? There's nothing you can kind of smash it into. We'll talk about radioactivity in chapter 3, which is a little weird, but essentially compounds can be broken down into the elements. The elements cannot be broken down further. So that's for substances or pure substances. You can also have mixtures, right? And our mixtures are going to have multiple substances that are in them, like a glass of milk, right? Has a bunch of stuff in there, right? It's got water, it's got lactose, it's got a bunch of other vitamin D, all kinds of things are in that glass of milk when you're drinking it, right? So our mixtures can be either homogeneous or heterogeneous, right? So the prefix homo means the same. Whoop. My pen. Sorry, my S looks really weird there. And hetero means different. Right? And this is just observational, right? So if you're looking at a mixture and it all looks the same, that's going to be a homogeneous mixture, right? So my chocolate milk over here, it all looks like one thing. I can't discern anything really different about it. That's a homogeneous mixture. But my cookie over there, I can clearly see those chocolate chips. And it's making me hungry for lunch, right? So that one is a heterogeneous mixture. You've got the baked part of the cookie, and you've got the chocolate chips, and you can see differences in there. Okay. So that's homogeneous, heterogeneous mixtures, right? And now we get to states of matter. States of matter are physical properties. So every substance has these three different states of matter that they can exist in. Doesn't necessarily mean that they reach those states on the Earth. Right? But you can have a solid state, you can have a liquid state, and you can have a gaseous state. So for water is very unique on our planet because it exists in all three states naturally on the planet. That's actually really rare. Like, if we find gold out there, it's pretty much a solid. We don't find liquid gold and gaseous gold. But you could make that in the lab. If you heat the gold up far enough, right, it'll melt. Right? And we do that, right? We like to wear jewelry and things, right? And get it into nice shape of a ring or something like that, or a tooth, right? Like you got a nice gold tooth, right? So you would have to melt it and then let it re-solidify, right, into the solid phase. So you can do phase changes with any substance, right? And it does not change the compound, right? That's a physical characteristic of that compound. Right? So you can melt it and then it resolidifies and it's still the same thing. All right, let's do a little practice. All right, I think I have to invite you again.
I just swiped over to it. It was there. Anything that occupies space and has mass. No, it's You submitted to me.
All right, do we have all the responses?
Did you put matter? Yeah, I put matter, yeah.
Yeah, so you all occupy space, you all have mass, and you all matter. Yes. 100%. Yay. All right, when an ice cube melts, this is an example of a physical or chemical property.
No explanation.
Oh, yeah, it's natural.
Yeah, we're not.
Oh, yeah.
Wait, we're confused.
Oh, it can melt.
Like, if it's not on heat, it's new to me, you know?
Yeah. So it's chemical. gotta write that out now because it's confusing me. Phase change is a chemical.
And we have all the responses.
Oh, so it's physical property. Oh, so you're manipulating physical property. It's physical property. Why you say chemical? No,
Yes, it's a physical property. So changes in state do not change the substance, right? So you can have a solid, a liquid, or a gaseous phase, and the compounds don't change. How about the process of cooking an egg? Can you uncook the egg?
So is that chemical?
Yes.
Yeah, you could like make a head.
And we have all the responses. Best guesses. All right, very good. All right, so if you had a marshmallow and you melt the marshmallow, what kind of change is that? Physical, right? It's just melted. It's gone from a solid to a liquid. What happens if it turns brown? It's burnt. That's a chemical change. Yeah, so heating can melt something, physical change, but it also can burn something or oxidize it or break it down. That's a chemical change. A substance that cannot be broken down into simpler components is called, or are called,
Yeah, every time that happens, the first one turn off your brain and start writing. Oh, yeah. Your brain's
All right, we have all the results. Very good. That's the elements. I think you guys like this chapter better than the math chapter already. Mm-hmm.
It's not gonna because the suit's gonna like change its shape, but the gas kind of just like floats in.
Mm.
Okay, I'll put on my results.
Wait, what did you do? Yeah.
So think of this in the terms of our room, right? This room has a certain volume to it, right? We obviously come in, we don't take the shape of the room, right? So solids are out, right? What if we started filling the room up with water and we filled it halfway? Would that fit this definition?
So it's gonna be gas. Oh man. What?
Right? Because the liquid is going to take the shape of the container, but unless you fill it completely full, it won't fill up the volume. But if I open up a tank of oxygen in here and let the oxygen out, it's going to fill up the room, right? It's going to go to all the spaces in here. So that's our gas. That's 5. All right. All right. So the next concept we get to are reactions, right? So this is chemistry or chemical changes that happen. So when we're looking at a chemical reaction, we're going to put more than one substance together, right? And it's going to have a reaction where those substances actually change their chemical properties, right? So they become different things, right? So on the left side of the equation, right, are going to be the reactants. That's what we would maybe put into the test tube. And then we let them react. And then the products come out. And so the products are shown on the other side of the arrow when you're looking at a chemical reaction. So in this reaction, you see a molecule of methane. And we'll get used to looking at these space-filling molecules of things and what they mean as we go through the class. And if we mix that methane with oxygen, and we have some catalyst in here, a spark in this case, it's going to burn that methane, and we would release carbon dioxide and water once that methane burns. So methane is a key component of natural gas, right? So we may be doing this in our homes, right? You may be using natural gas to heat your home, right? The natural gas comes in, you've got a spark inside your heater, right, that will light that natural gas on fire, right? And the oxygen is needed for things to burn. And then you would form carbon dioxide and water on the outside, and that would be the emissions coming out of your heater. And another product of our reaction that's not shown in here is heat, right? So the heat's coming out on the product side in this case, and we're benefiting from that if we're heating our homes with that. Okay, so that's a chemical reaction, right, that we see there. So the stuff on the left side are called the reactants. That's what we're putting into the tube to react with each other. And then the stuff on the right side are the products that are coming out, right? So you've got both of those. So when we have chemical reactions, whoops, go farther. All right. We have certain laws that we have to obey, right? So we have the law of conservation of matter, right? So matter cannot really be destroyed during a reaction. It's just going to change shape. It's just going to change features. So whatever we put in on the reactant side has to come out on the other side. We're not going to lose elements. We're not going to lose atoms in that reaction. Right? So it can't be created or destroyed. It just is rearranged. So that's the conservation of matter. So what we put in, we have to make sure we get out on the other side. It may be rearranged and changed, but all of those atoms still have to be accounted for on both sides. So we have to have the same number of atoms of each element on the right-hand side as the left-hand side of the equation. Right? So if we come back and look at our equation, right, I can see my oxygens. I've got 2 oxygen molecules. Each of those molecules has 2 oxygen atoms in there. So I have 4 oxygen atoms on this side. If I look over here on this side of the equation, the oxygens are all red, right? So I can see now that compound has 2 oxygens, and each one of my water molecules also has an oxygen. So there's 4 oxygens on the other side of the equation. That obeys my conservation of matter for the oxygen. And we can also check the hydrogens, which are white. There's 4 on my methane right now, and there's 4 in my water that's made. And then there's 1 carbon making my carbon dioxide and 1 carbon from my methane. So this is a balanced chemical reaction that obeys the conservation of matter, right? What goes in on one side has to go out on the other side. The energy that I told you about too, this releases energy on the product side. It's got to suck that energy from this side and use it to make that energy release. So when you have chemical substances that are going into the reaction, these subscripts here indicate how many atoms of the element are in a compound. So my oxygen up here, right, each oxygen molecule has 2 oxygens in it. That's defined by that subscript, right? So when I have 2 molecules of oxygen, right, that's described by the coefficient in front of there, right? So I have 2 molecules of oxygen in this as well. So the one on the top, that's 1 molecule, that's 2 molecules, and that goes with the coefficient. The 2 atoms, right, of oxygen go with the subscript, right? So if they're bonded together, they get the subscript. If there's multiples of them, they get a coefficient. So if a coefficient is not shown, it's 1, right? So my first one out here, right, I can assume that there's a 1 out there because there's only 1 molecule of methane. My methane molecule has 1 atom of carbon, so I don't have to show that subscript because there's only 1. That's implied. And then there's 4 atoms of hydrogen in there, and that is the subscript for my hydrogen there. All right, so on the other side, we could do the similar thing. That carbon shown here, there's 1 of those, and there's 2 oxygens. That's the subscript there. And same for the water, right? So there's 2 hydrogens shown by that subscript. There's 1 oxygen, and so there's no subscript shown, but it could go there if you put a 1 there. Ooh, that's terrible. Right, so it's implied when there's not 1 shown that it is 1. And then there's 2 molecules of this that are here. That's the coefficient. All right, so that's a chemical reaction. We'll see more of these as we go along. This is just an introduction to it, to what those coefficients and what those subscripts mean. We'll learn how to make like real molecules and that are balanced and correct in chapter 4 and 5. So that's kind of down the way, not the first exam. But I like to introduce just the reactions first, just so you've seen them and kind of know things happen like that. Okay. Oh, this is so small. Here's the reaction. All right. So. All right, so it's asking you the sodium sulfide, which is, which is this guy here. They're asking you, is it a reactant or a product? Very good. We have all the responses. Maybe 2 questions left. Hold on. Yep. In the compound P4O8, blank atoms of phosphorus are bonded with blank atoms of oxygen. This is not a trick question. And just a note with your elements on the periodic table, all of the abbreviations for the elements, like your periodic table has the elements written underneath in each box, so you can look and say, oh, Be is beryllium. You'll notice that the first letter is capitalized. That is always true. So you always have to have a capital letter for your elements when you're writing them out. If it has a second letter, it's always the lower script when you're writing that. So just make sure when you're writing your element symbols that you're following what's on the periodic table. Capital letters, always the first one. If it has a second one, always lowercase, so you don't make a mistake and put two together that are actually two different elements when you only mean one. All right, let's see here. 4 and 8, very good. And our last one for the day. In the following equation, which is tiny again, what should the coefficient be in front of the oxygen? Little bit harder. Right? So we need to see how many oxygens are on the other side, because we need the same number on the reactant side. So what are you seeing in that first molecule here? So you've got 7 CO2 on this side and 8 waters. Right? And on the other side, we have C7H16 plus the O2. And we need to know how many O2s do we need to make what's on the other side. So if each CO2 molecule has 2 oxygens, and we have 7 of them, how many oxygens are in this one? 14? Yes. So 7 times 2, 14. And for 8 waters, how many oxygens are in this one? 8. So on this side, how many oxygens should I have total? 22. So there's 22 oxygen atoms over here. Currently, I only have 2 per oxygen molecule over there. So how many oxygen molecules am I going to need to get 22 atoms of oxygen? Yay. Very good. All right, I will see most of you on Friday. If you're online, I will see you next Monday.
I'll text you when I'm done. I'm pretty sure it's